Okay guys, in this video we are going to be looking at molecular structure and something related to molecular structure called polarity. The model that we're going to be using for predicting molecular structure is called the valence shell electron pair repulsion theory, or VSEPR for short. So molecules, they have a three-dimensional geometry. In the case of formaldehyde here, we have, there's different bond lengths, and then notice that, there's a bond angle. That is, there's an angle between the hydrogen, carbon, and hydrogen. It's not 180 degrees, it's not 90 degrees, it's 118 degrees. And so in this topic, we are going to try to figure out a way of predicting, roughly speaking, what different geometries we should expect for small molecules. And so this Vesper theory uses a simple rule to help us predict what the geometries of a molecule should be. And the idea is that the bonding electrons that make up these two covalent bonds, actually I should say the three covalent bonds, right? The bond between carbon and hydrogen, this carbon and hydrogen, and this carbon and this oxygen. The idea is that these electron pairs are repelled by one another. And so the molecule tries to adopt a geometry that will minimize that electron repulsion. Okay, so the idea is that the bonds, they want to get as far away from each other as they can. And that's what leads to the molecular geometry that's observed. Okay, let's look at some different scenarios here. So this table is something that you need to commit to memory. What it conveys are the basic Vesper geometries. Okay, so consider a molecule like beryllium dihydride that has two bonding pairs. There's a bonding pair from beryllium to this hydrogen and a bonding pair from beryllium to this hydrogen. Okay? Now, in order for these electron pairs to get as far away from each other as they can, the molecule will adopt a linear geometry, a linear Vesper shape, where the electron pairs are separated by 180 degrees. Okay? So you need to know the shape, the name of the shape, linear. You need to know the bond angle, and then you need to have this picture in mind when you talk about that shape. If we consider a molecule like boron trihydride, which for this example is electron deficient, boron trihydride has three bonding pairs. Right? We've got one for this boron hydrogen bond, one for this one, and one for that one as well. So when you have three bonding pairs all attached to the same center electron, in order for the electrons to get as far from each other as possible, the molecule forms this little equilateral triangle where all of the bond angles will be 180 degrees. And we call that a trigonal planar structure. Okay, so this is the trigonal planar Vesper structure. When you have four bonding pairs, like you have in methane here, the molecule adopts a tetrahedral shape, okay, and it's no longer planar. In this diagram here, this molecular structure diagram, these two hydrogens, where you have just the narrow line, these two hydrogens are in the plane of the page, that is the plane of the screen, whereas this one is coming out of the screen at you, and this one with the dashed wedge is going back behind the screen. And so you can think of this molecule as forming a little tripod. Okay, this hydrogen, and that hydrogen, it's a little tripod, and then this hydrogen sticks up top. So this is the tetrahedral structure. All of the bond angles here are 109.5 degrees. In this phosphorus pentafluoride structure, here you've got Well, let's look at the triangle here in the center. So here we've got a set of 3 fluorines that are coming. One of them is in the plane of the screen. One of them is coming out at you, and the other one is going back into the board. So this is a perfect equilateral triangle right here. And then both on top and below that equilateral triangle are more fluorine atoms. This is called the trigonal bipyramidal structure. Right? You have a little pyramid up top and then a little pyramid down below. So a bipyramid. Within the plane here, or I should say within this trigonal plane, you have 120 degrees between the fluorine, phosphorus, fluorine bonds. However, when you go from the axial position down to the equatorial position, that's a 90-degree difference, 90-degree bond angle. So there's 2 bond angles you need to know about for the trigonal bipyramidal structure. Inside this plane here, it's 120, and then going from the axial positions down to the equatorial positions, it's 90 degrees. So the trigonal bipyramid. For this sulfur hexafluoride species, okay, we've got 6 bonding pairs. The structure is called octahedral, and it forms a little square. Okay, so in this diagram, 2 of the corners of the square are coming out at you. The other 2 corners of the square are going back behind the screen. Within the square, of course, okay, the bond angles are 90 degrees. And then also from the equatorial, from this position to that position, it's also 90 degrees. And then this fluorine, sulfur, fluorine is 180. This fluorine to sulfur and that sulfur to fluorine, those are 180 degrees as well, right? So this bond angle and that bond angle are, I should say, this bond and that bond are 180 degrees apart. This bond here and that bond there, those are 90 degrees apart. Okay, so that's the octahedral structure. So two electron pairs gives you linear, 3 electron pairs gives you trigonal, 4 electron pairs gives you tetrahedral, 5 electron pairs gives you the trigonal bipyramid, 6 electron pairs gives you the octahedral structure. You need to know the structures and their bond angles and their names. What about lone pairs? Right? Not all electron pairs are bonding pairs. We also have lone pairs. Lone pairs take up a bit more space than bonding pairs. Okay, so this leads to deformed geometries or distorted geometries. I'll give you an example here. Methane. Okay, we've got 4 bonding pairs. And so methane is a tetrahedral shaped molecule. In ammonia, NH3, there's a lone pair. And so there are a total of 4 pairs. So the parent Vesper structure is tetrahedral, but the lone pair of ammonia takes up a little bit more space than a bonding pair would. And so as a consequence of that, that lone pair of electrons, that squeezes the bond angles down a little bit. So it's not quite 109 degrees, it's a little bit less. 106 degrees in ammonia. Triple bonds tend to take up more space than double bonds. Double bonds take up more space than single bonds. Double and triple bonds also lead to slightly distorted geometries. I'll give you an example that we've already seen. Right, this double bond right here, compared to the carbon-hydrogen single bond, it takes up a little bit more space. And so what that does is it squeezes these carbon-hydrogen bonds together a little bit more. Okay, so you don't have a perfect 120 degree bond angle here. It's 118. We want to be able to use this Vesper model to predict the geometry for simple molecules. And the way you do that, first you need to write down the Lewis structure, and then you need to count the number of electron pairs around the center atom in your Lewis structure. And when you come across multiple bonds, you treat the multiple bond as if it were only one electron pair, even though it's actually more than one electron pair. as far as Vesper is concerned, you can treat it like one electron pair. Once you've counted the number of electron pairs, you then determine the parent Vesper structure, and then depending on which electron pairs are lone pair electrons and which are bonding pairs, that leads you to specific molecular geometries, which I am going to show you next. So this is another table that you need to commit to memory. It has the same information that we've already looked at, that is, it has the same basic Vesper structures, but there's also subcategories that we need to know as well. So in this diagram here, when you have two electron pairs around the center atom, that's always the linear structure. If you had 3 electron pairs, there's 2 possibilities to consider. In one possibility, all of the electron pairs are occupied with another atom, right? So you have an AX3 structure. But you could also encounter a structure where you have 3 electron pairs, but one of the electron pairs is a lone pair, and the other 2 involve atoms. We call this the bent or angular structure. Typically, it's called the bent structure. And what you'll find is that the bond angle here is going to be less than 120 degrees. That is, the lone pair is going to push and make this bond angle smaller. We've already looked at the tetrahedron structure. Well, what if one of these atoms were replaced by a lone pair? That gives us this trigonal pyramid. Okay, so the name of ammonia, this is what ammonia looks like, where A would be nitrogen and X would be hydrogen. There's a lone pair. We would call ammonia the trigonal pyramid. It's not a tetrahedral structure. Its parent Vesper structure is tetrahedral, but the lone pair distorts the geometry, and we call it the trigonal pyramid. If 2 of these atoms were replaced with lone pairs, this would be the case for water, right? If A were oxygen and the 2 X's were hydrogens, the oxygen would have 2 lone pairs on it. So we still have 4 electron pairs, so the basic Vesper geometry is tetrahedral. But when 2 of those electron pairs are associated with lone pair electrons, we call it the bent shape. Okay? It's the same name as we had before for the trigonal planar, where one of them is an electron. One of the electron pairs is a lone pair. So the same name is applied. Here is the trigonal bipyramid structure. If we replace one of the X atoms with a lone pair, we get what's called the seesaw or sawhorse structure. I usually call it the seesaw structure myself. Here they've put the seesaw the incorrect direction. You would need to rotate this figure by 90 degrees to make the seesaw structure. But in any case, that's what it's called. If you replaced 2 of these atoms with lone pairs, it gives us this T-shaped structure. Okay? Again, the T is sideways. If you replaced 3 of them, 3 of these atoms with lone pairs, it would give us a linear geometry. Okay? So this is called linear. Starting with the octahedral structure, replace one of the atoms with a lone pair. This gives us what we call the square pyramid. This is the base of the pyramid. These atoms are the base of the pyramid, and here's the top of the pyramid. Okay, so a pyramid with a square base. If you replaced 2 of the atoms with lone pairs, you get what's called the square planar structure. Okay, so it's just a square and it's flat. That's why it's called square planar. The electron pairs go above and below the plane. Replace 3 of them with lone pairs, it gives you another T-shaped structure. Replace 4 of them with lone pairs, and it gives you a linear structure. Okay, so you need to commit these structures and their names to memory so that you can correctly identify the molecular geometry of simple molecules. And so we are going to go through several of these. Okay. So it's critical that you can write the Lewis structures, because if you can't get the correct Lewis structure, then you can't determine the correct number of electron pairs, and you'll never be able to get the geometry if you don't know that. So I'm going to go through these, and then unless there's one that I don't know, I won't go through the full generating the Lewis structure. I'm just going to write them down just because I've seen them so many times. So for carbon dioxide, this is the Lewis structure. Okay. And we count the double bonds. We just count those as one electron pair. So here we have 2 electron pairs. Right? Recall from our discussion of the Vesper geometries, that would be a linear arrangement. Okay? So CO2 is a linear molecule, 180-degree bond angle. For part B, we have an electron deficient species. So boron trichloride. What geometry should it adopt? Well, we have 3 electron pairs. And so this should be a trigonal planar structure. And so most people, when they draw this molecule, when they draw the Lewis structure, they're already anticipating that it is trigonal planar. And very frequently, they'll just draw it as such. Okay, so trigonal planar. It's a flat molecule. The bond angle's 120 degrees. For part C, we've got the carbonate ion. I believe we'll have one like that, and then we'll have these guys here. I'm not going to put on the extra electrons. Well, I should. I'm going to go ahead and do it. It's going to look like this. So here's the carbonate Lewis structure. You can see that I've already drawn it in the geometry that it should have. There's 3. We count the double bond as 1 electron pair, so there's 3 electron pairs around the center carbon atom. And so it's going to be, again, a trigonal planar structure. What do you think the bond angles are going to be? I'm going to focus on this bond angle. Right? Well, a perfect trigonal planar structure would have 120 degrees. But this double bond takes up a bit more space than an ordinary single bond would. And so what that's going to do is it's going to squeeze that bond together. So we would imagine that this bond is going to be a little bit less than 120 degrees, and then this bond is going to be a little bit greater than 120 degrees, because the double bond repels the other bonding pairs a little bit more. Let's look at ammonium. Ammonium is going to have 4 bonding pairs, and it's a cation. So that's the Lewis structure for ammonium. We have 4 bonding pairs. When you have 4 bonding pairs, and so 4 electron pairs, and they're all bonding pairs, that is, they all involve another atom, we would call that the tetrahedral structure. Okay, and so it's actually a 3-dimensional. It's not flat, it's not planar, like it's drawn here in the Lewis structure. Lewis structures don't convey 3-dimensional structure. To give it a sense of what the 3-dimensional shape looks like, you do it like this. You put your center atom there. These 2 hydrogens are in the plane of the page. And then you're going to have one coming out of the plane, so you use a solid wedge to denote that one. And then one is going to be going back into the plane, like that. Okay. And then all of the bond angles are 109. I've already forgotten the decimal. It's 0.5 or something like that degrees. Okay, so this is how you represent the actual 3D structure using pen and paper. You use these wedges. And you'll see a lot of this in organic chemistry if you're going that far. Let's do some more. Let's do phosphorus pentafluoride. Okay, so this is going to be a hypervalent Lewis structure. I'm not going to put the extra electron dots on the fluorines, but this is the correct Lewis structure for the center atom. Each of the fluorines would have an octet. We have 5 electron pairs. Okay, so when you have 5 bonding pairs, this is the trigonal bipyramid. And here's how you can draw it in kind of the way it would look three-dimensionally. You would put that fluorine in the plane, this fluorine in the plane of the page, and this one coming down. And now you need to get 2 more in there. One comes out of the plane of the paper, and then another one goes back behind the paper. Okay, so this is the trigonal part. And then, so we typically would call these equatorial, and these would be called axial. The bond angles inside the plane are 120 degrees, and then the bond angle from this fluorine down to that one, that would be 90 degrees. Let's look at water, H2O. Okay, the Lewis structure for water looks like this. So you have 4 electron pairs. And when you have 4 electron pairs, the parent geometry is tetrahedron. So it's a tetrahedral Vesper geometry. However, 2 of the electron pairs are not occupied with atoms. They're lone pairs. Okay? And in that case, we call it a bent structure. So this is a bent geometry. The bond angle is going to be less than 109 degrees. I think it's something like 104, if I'm not mistaken. For hydronium, H3O plus, the Lewis structure will look like this. Again, we've got 4 pairs of electrons around the center oxygen. This time only one of them is a lone pair. And this we call the trigonal pyramid. And it would look like this. We typically would draw it with one hydrogen coming out like that. This one's the lone pair, and then this goes behind the plane, and that one goes behind the plane. Okay, and the whole thing has a plus charge. What do we have next? Sulfur tetrafluoride. Here's one where I probably need to start working out the Lewis structures correctly. So sulfur has 6 valence electrons plus 4 times 7. Right. Each fluorine has 7, so we've got 28, 29, 30, 31, 32, 33, 34 electrons. So we'll make sulfur in the center, and we'll put the fluorines going around. We'll make our skeleton bonds. So 2, 4, 6, 8. So that's going to be, what, 26 electrons to go? Yeah, that looks right. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Leaving us with 2 to go onto the sulfur. So how many electron pairs do we have around the center atom? 1, 2, 3, 4, 5. 5 electron pairs. The parent structure is the trigonal bipyramid. However, when we have one of those is a lone pair, we call it the seesaw structure. And so just to clean it up a little bit, I'll make this the lone pair. I've got a fluorine up that way, a fluorine that way, fluorine this way, and then a fluorine going back behind. Seesaw structure. Let's look at the xenon difluoride. Again, this is going to be another one that I'm going to have to count out. Xenon has 8 plus 2 times 7. So we've got 14 plus 8, 22 valence electrons. Let's put the xenon in the middle, fluorine out like that. We've just taken up 4 of them. So we're going to have 18 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Leaving us with 6 more. 1, 2, 3, 4, 5, 6. So here we've got 1, 2, 3, 4, 5 electron pairs around the xenon. So the parent structure is the trigonal bipyramid. However, when 3 of them are lone pairs, it's a linear structure. So it's a linear molecule. If you wanted to draw it in the trigonal bipyramidal structure, you'd put the xenon here. You could put the fluorines in the axial positions, and then you'd have lone pairs there in the plane, a lone pair coming out of the plane, and a lone pair going back behind the plane of the page. For the xenon tetrafluoride, again 8, 4 times 7, so we've got 28 plus 8, 36 electrons that we need to deal with. Put the xenon in the center, fluorine. We'll make those. We'll make our skeleton bonds. So 2, 4, 6, 8. So that would be what? 28 electrons to go. Leaving 4 more. 1, 2, 3, 4. How many electron pairs do we have around the xenon now? Well, we've got the 4 bonding pairs and the 2 lone pairs. So we've got a total of 6. Okay? The parent structure is the octahedral structure. But when 2 of the electron pairs are lone pairs for an octahedral, we call it the square planar structure. And there's different ways to draw it. Draw it like this. These fluorines are coming out of the plane of the page. This one is going back behind, as is that one. And then we've got the lone pairs above and below. This is a fun exercise, and it's here what we're doing. It's relevant to biochemistry if any of you are interested in that. Here we've got two molecules, and what we're being asked to do is to apply the Vesper model to predict what is the local geometry about each of these atoms here. Okay, and so I'm just going to quickly draw the structure, at least the first one. I can leave the other one for you as an exercise. And then we've got this here. Okay, so what is the local geometry about this nitrogen? We've got 1, 2, 3, 4 electron pairs around this structure. Okay, and so the parent geometry would be tetrahedral. However, because one of them is a lone pair, we would say that that is trigonal pyramidal. About this carbon atom, we've got 1, 2, 3, 4 electron pairs. They're all attached to an atom, and so we would say that that locally is a tetrahedral. I'm spelling it wrong. Tetrahedral geometry about that carbon atom. Here we've got 1, 2, 3, right? The double bond counts as 1, so 1, 2, 3. That's a trigonal planar. So about that carbon atom, it's trigonal planar. Here we've got 1, 2, 3, 4. 2 of them are lone pairs, so this is going to be a bent structure about that one. And then you can use that to estimate what the geometries are going to be. So you get the bond angles, for example. So here, the bond angles are going to be pretty close to 109. Not quite. They're going to be smaller. Here, they're going to be pretty close to 109 degrees. Here, the bond angle is going to be pretty close to 120. And here, it's going to be less than. Here, it'll be less than 109. Okay, so you can use your knowledge of Vesper and Vesper geometries to picture in your mind what the shape of a complicated molecule would look like. I'm going to go ahead and leave this second example alanine over here for you to try on your own. And I think with that, I'm going to go ahead and stop this video. We'll pick up the polarity and the dipole moment discussion in the next one.